Hello, everyone. Good morning, good evening. I'm Thiago. I'm project coordinator here at Encora Brazil Division, and I'm pleased to be your host today. This session is fine-tuning LLMs, what it is, and how to do it. Two quick notes here. Please follow us in the social media that appear in your screen. This session is part of Global Dev Week organized by Encora, so thanks Encora. You can interact by chat, and the speaker will be happy to answer also using the chat. Okay? With further delay, the speaker of this session is Ana Robles. Ana is a machine learning engineer with expertise in system architecture, API design, database integration, and performance optimization. Anna is currently leading one of Encora's generative AI teams, working on how to best integrate LLMs with the other MLs, systems, and software tools to create software agents with multimodal capabilities. Hello, Anna. The stage is all yours.
Thank you so much. Hi, everyone. Happy Tuesday and welcome to my talk. Today, we are going to talk about fine tuning large language models. So, let's start with this. I'm going to share with you my screen. So, now that we can see it, so the agenda for today is like we're going to have a small overview where we are going to cover what it is fine tuning, how to do it, the advantages, the approaches to fine tune. Then we are going to dive in on those approaches that are instruction tuning, alignment tuning, and efficient tuning. So let's start with the overview that is fine tuning. So, what is fine tuning? Fine tuning is a process that takes a model that's already been trained for a given task and then tuning that model to make it perform to a second but similar task. So, we are basically using the knowledge that was gained from solving one problem and then apply it to a new but related problem. And this concept is something that we see every day when we want to try something new. It helps us if we have done something similar before. So you might wonder how to fine tune. And the first thing that we need to know is like we need to find a pre-trained model that already solve a task that is similar to ours and make a copy of it. So if you want to create, for example, a conversational model as this one that we saw in here, we can use the pre-trained model GPT-3. So this model is already been trained on task completion, language translation, and some other tasks. So now that we have this model, what we need is to have a domain-specific data set that is how do we want to our new model to behave. So in this, we will have some training examples, some instances that are going to help us to train that model. And what are we gonna do basically is like we are going to use the learned weights as a starting point for the base model, and those weights are going to start to be updated. So we keep the training, those weights keep updated, and we do this until we are happy of having this result. So why you might wonder like why we would like to do this if we already have these beautiful, powerful, large language models. And as many people say, we already have ChatGTP, but ChatGTP is not the whole thing. We have like a lot of a lot of models right now, and they have become more sophisticated with time. They are really capable, they are versatile, they can handle a wide range of tasks, but this also means that they are not specialized on any specific task. So if you have play around and you wanted to use it for something in specific, you might notice that you cannot rely just on the inputs you have, because small changes cause they have like this huge impact. So we might need to improve the quality of the responses so you can get it like in a consistent way. And that's when we need to tune the model, and we will end up with this model that is specific for what we want, and we are all happy. So uh, maybe you have asked why not just to do it from scratch. I mean, if we know it's going to work, why not just to build a model from zero? And well, that's exactly what we're trying to avoid. Building something from scratch, it will imply a lot of decisions, and well, we will have waste of time, computer resources. It's not a secret that training these models is like really expensive. So another of the advantages for fine tuning is that it requires way less data than before, because the model that we have already have learned some general features, and also it will be faster to deploy, and you don't have to retrain the entire model and a lot of its many weights. And another huge thing to mention here, besides these five things in here, is that there is a lot of cases where fine-tuned models outperform generalist model. And in here I have two examples of them. One is Goat and the other is Gorilla. They are both examples for Meta, and they are both fine-tuned another model from Meta called Llama. So GOAT stands for Good at Arithmetic Task, and this one outperforms GPT-4, that is this huge and powerful model on this task. As for Gorilla, Gorilla is quite similar to Toolformer. It works with external tools, and this one outperforms not only GPT-4 but also Cloud. That is another huge model, and is better to handle multiple API calls. And these are only two examples. We have seen a lot of scenarios when this same thing occurred. So by this point, we have seen that fine tuning is like wonderful, has a lot of advantage, is exciting. So what we're waiting for? And the thing is, like in here, we can have like multiple approaches. I'm gonna mention three of them: instruction tuning, alignment tuning, and efficient tuning. I want to highlight that these approaches, even they are different, they can be complementary. You don't need to choose just one. So if you use a combination of them, they can help you to enhance the different aspects of a language model. So let's start with instruction tuning. And instruction tuning, we have that is an approach to fine-tune pre-trained LLMs on a collection of formatted instances in the form of natural language. And what does this mean? Okay, so this is focused on the dataset part. So we have these instances that are composed, as you can see in the example, and by a task description. That one says, please translate the French to English. We will have some demonstrations. The demonstrations are optional, but they are like a good thing to add. In these demonstrations, as you can see, we have this obviously beautiful French phrasing there that I'm not going to read, and its corresponding English translation. So beside the task and the demonstration, we have the input-output pair, that is what we want to give the model and what we want the model to give us. And well, the importance in the instances in here is like if they have good quality, the performance of your model will improve. So we need diversity on the task. And what do I mean with diversity? It could be diversity in the length, in the structure, in the creativity of your sentence. And also it's important to know that the diversity of the instructions is way more important than the number of the instances. Also, we also have noticed for some studies that incorporating other components, this meaning things to avoid or suggestions that you can do to the model, it will have like a small effect on the model, so you can avoid those. We also have some strategies as we want to have these diverse instances. We need to balance the proportion of different tasks during fine tuning. So a widely used method is the examples proportional mixing strategy. And this is like combining all the data sets and sampling each instance equally. But also we can set a maximum cap to control the maximum number of examples. This is basically a setting. So we are limiting the data sets. And this will prevent the larger data sets to overwhelming the entire distribution. And that's one strategy. And the other one is combining instructions for tuning and pre-training. So for now, we have seen like we have this model that is already trained, and then we make the fine tuning. In this step, we have some other studios that trying to like make a mix of both of them, in where we have like we are going to have this kind of instruction tuning as part of the general corpora to pre-train the LLM from scratch. As some examples for this, we have COPT EML, GLM 130B, and Galactica. And well, that's for strategies. The last thing that I want to tell you about instruction tuning is that something that is really cool about instruction tuning is that it can generalize to relate tasks across languages. So this means that if they acquire this general skill for an English-only dataset, they can transfer such a skill to another language. And of course, this reduces a lot of effort of instruction engineering for a specific language. As for the scale, all models benefits when doing this instruction tuning. Doesn't matter if your model is small, is a large one, is a huge one, they all benefit. So that's everything for instruction tuning. Then let's bring alignment tuning now. So alignment tuning, the reason that we care about alignment tuning is that sometimes the models exhibit unintended behaviors. And with this, I mean fabricating false information, producing bias expressions, and some others. So we need to try to do something to try to align the LLMs to act in line with human expectations. So, as you can imagine, this is huge, and there are a lot of factors to consider in here. And you can see these criteria are quite subjective, but I'm going to tell you about three of them. There are like the representative ones. The first one is helpfulness. And this one tells us that the LLM should demonstrate a clear attempt to assist the users in solving their task or answering questions in a concise and efficient manner as possible. Then we have honestly. Honesty tells us that the LLM aligned to be honest should present accurate content to users instead of fabricating information. And this refers to when the model tends to hallucinate, that it start creating responses out of the blue. And then we will have harmlessness. And for this one, the language produced by the model should not be offensive or discriminatory. In fact, ideally, when the model was induced to conduct a dangerous action, the LLM should politely refuse. And I added as a note in here that, of course, what is considered good or bad, if you want to see it that way, it will vary among the individuals, the societies. It will depend on who is using the LLM, the type of question, and the context of the question. So just for you to have a general idea, the way that this is learned by the model uses three principal elements. That is the model that we want to align, a reward model, and a reinforcement learning algorithm. So that's everything for align tuning. Let's pass to parameter efficient tuning. That is our last one. And till this point, we have seen that with instruction tuning, you can have a better performance. And with alignment tuning, you can have responses that are more human aligned. So you might wonder why making fine tuning efficient is important here. And if I had to put it into phrases, I would say like it's expensive to train and it's not necessarily eco-friendly. So as we said at the beginning of this talk, we mentioned that these large language models have been increasing in parameter size and data. And for us, what will imply is like if we want to fine tune these models, we will be needing bigger GPUs and multiple GPUs, which in summary is really expensive. So, parameter efficient fine tuning or PEF involves optimizing the model's architecture so it's easier for us to fine tune. And this is this is done by doing this extra step, and this extra step is modifying the existing network. So how our fine-tune process will like? This modification is, it can be like in many ways. There is a whole area in PEF to solve this, but I'm going to mention a couple techniques later. For now, just to have in mind that this is like if we were adding an extra layer. So in here you can see we have an original network, and then if we want to modify that, let's say we add this extra layer. Yeah. So I know we are adding this and this might sound like more work, but the thing here is like we don't need to train the whole thing as we say before. Now we are just focusing on the thing that we add, on the thing that we inject. So our fine-tune process now it will look like we are going to find this pre-trained model, we are going to add this new extra layer, and then we are going to start training with the data sets that we have for our specific task, and we are going to have the rest of the original model frozen. So what this thing is going to do is like it's going to be only updating the weights for the new thing that we added. So in here we have a fine-tuning representation. We have the inputs, what is going to be frozen, that is the pre-trained weights, and what is going to be updating. And well, we will review some PEF methods for transformer models. For those who aren't related with transformers, don't worry, transformers are just a type of neural network architecture. This was invented by Google, and most of the large language models now use as a base that architecture. Sorry. So here are a list of methods or modifications that we can do. I'm going to mention some of them, and then we're going to dive in on LoRa, that is one of the most popular these days. So we have the adapters. The adapters are the green ones that you see there. So adapters incorporate a small neural network models. First compresses the original feature vector into smaller dimension, as you can see in the smallest image, and is followed by a nonlinear transformation, and then it recovers to the original dimension. That's the adapter. We can also have prefix tuning, and this prefix tuning adds a sequence of prefixes that are task specific, in which are set of trainable continuous vectors. And just to spoil a little bit, we have LoRa. That LoRa imposes a low rank constraint for approximating the update metrics at each layer, as to reduce the trainable parameters for adapting downstream tasks. So we will see LoRa on DeepEye. And LoRa started as a hypothesis based on another work. In this paper that you see on your left, this one suggests that when you have a pre-trained model and we adapt it to a specific task, we can describe the model almost as accurately using way fewer dimensions. So let's say we have 50 dimensions. Maybe it could be described only with 20 of them. So we just can get rid of the extra and we are going to be good. We are not going to lose like that much performance. So based on this work, LoRa hypothesized that the weight also have low intrinsic rank. So rank is not the same as a dimension of a matrix is not necessarily the same. It is usually less than that. So they are hypothesized. They have this hypothesis when they say we have this low intrinsic rank. Rank is just a property in the matrix that tells us about the number of linearly independent row and column vectors. So having this concept of rank and the concept of matrix decomposition, we obtain LoRa. So we are going to use this concept of matrix decomposition to represent this very large matrix A by B as a smaller combination of matrices. So as for LoRa adaptations, something that I wanted to represent in here is like instead of having this way update, as you see there, we are going to use the matrix decomposition. We are going to have the two smaller matrices. And I know that we are representing like the same stuff, but the reason that it helps us is because imagine we have a matrix before that it was 100 by 100. Then we will have 10,000 elements. So now let's say we have in these reduction matrices, we have 4 by 100 and 100 by 4. Then we will only have 800 elements to train, which is way smaller. And that's the idea of LoRa, that you don't need as much information to represent everything accurately. So how do we apply this into the transformer that we saw before? This trick, if you want to see it this way, can be applied to any metrics really. But in this work, they chose to apply it only to the adapting to the attention weights. And something really nice in here is like we have this small change that is really a representation, but in impact, LoRa performs better than other approaches, including full fine-tuning. And full fine-tuning, it will be this initial fine-tuning that I talked to you about, that is like without making any modifications, that is expensive and those things that we don't want. And you can see on the table that we have LoRa outperforming GPT-3 full tuning in there, and you can see the level of accuracy, and I think it's really crazy because they have this million of parameters for the full tuning, and as for LoRa, they only have 37, and they are winning. And if you can see in there, we have like the other version of LoRa that has less parameters, and it almost reaches the same level as the full tuning. So this is crazy, and this is where the benefits come, because now that we have less parameters, we have a reduction in memory and storage usage. And something that is cool is that now that we are injecting these new matrices, this pre-trained model can be shared and used to build many small LoRa models for different tasks, because we just need the original one and the LoRa's one. And as we have this, we can switch between the tasks. And the advantages of having the original ways is that it helps us to prevent catastrophic forgetting. That is when you fine-tune too much a pre-trained model, that the model just forget what he was doing before. So that's a huge advantage. And well, this is basically LoRa. Another thing that we have and that I wanted to talk to you about is like from this work, we have reached like a lot of other work. And in here, I want to mention that LoRa was created on 2021. And this is today's work. We have QLoRa, and also we have LoRa, and in here you can see that QLoRa it was work for the last month, and LoRa was work for the last week, and they both are very impressive. QLoRa, what does is like it reduces the memory usage that well that allow us to fine-tune a 65 billion parameter model on a single 48 gigabyte GPU, and it preserves like the full 16-byte fine-tune task performance, which is it's just crazy. And as for the LoRa technology, this one enhances LoRa by adding a generalized prompt model to optimize pre-trained model weights, and it also adjusts intermediate activations. So this will provide more flexibility across the diverse tasks and the datasets. And these are, as I told you before, some examples of the work based in LoRa. And with this, I'm going to wrap up the whole session. So as for now, we have covered an overview of fine-tuning. We enter deeply in some of the approaches that we have for fine-tuning: instruction, alignment, and efficient tuning. And this covers today's session. So it was a very active half hour. I hope you enjoy it a lot, and thank you very much.
Thank you, Anna. Excellent presentation, very clear and elucidative. Really, really good one. Thank you.
Thank you.
Thanks to all of our audience for the time and messages. I hope you've enjoyed. And please remember to return to the official website to review the agenda for the next session. I hope to see all you soon. Bye bye.
See you. Thank you.